Now, let's see about orifices. Orifice is a small opening of any cross section. So orifice is an opening of any cross section. It can be circular, triangular or rectangular. It can be placed on the side or at the bottom of a tank. That means anywhere through which fluid is flowing. A mouthpiece is a short length of a pipe which is 2 to 3 times its diameter in length, fitted in a tank or vessel containing the fluid. Orifices as well as mouthpieces are used for measuring the rate of flow of fluid. So before we have seen venturimeters which are used to measure the rate of flow. So here we are seeing two devices, that is orifices and mouthpieces. Orifice is one, then you have mouthpiece for measuring the rate of flow of fluid. So orifice is a small opening, that is a hole on the side or bottom of a tank which has fluid. So fluid can flow through this opening or hole. It can be of cross section, rectangular, circular or triangular. And mouthpiece is a small piece of pipe which has a diameter which is 2 to 3 times the length. That means the pipe has short length and large diameter. That is, diameter of the mouthpiece pipe is 2 to 3 times the length of the pipe. That means the pipe is short in length and large in diameter. Okay, so both these devices, orifices as well as mouthpieces, are used for measuring the rate of flow of fluid. Next, let's see the classification of orifices. The orifices are classified based on the size, shape, nature of discharge, etc. Okay, so first, depending on the size of the orifice, it can be classified as small orifice or large orifice. Okay. So if the head of the liquid, head means height, if the head of the liquid from the center of the orifice is more than 5 times the depth of the orifice is called small orifice. If the head of liquid or height of liquid is less than 5 times the depth of the orifice, it is known as a large orifice. Again, depending upon the cross-sectional area, orifices are classified as circular, triangular and rectangular. Again, depending on the shape of the upstream edge of the orifice, it is classified as sharp-edged and bell-mouthed orifice. Again, depending on the nature of discharge, it is classified as free discharging and drowned or submerged orifice. Okay. Again, they can be classified as fully submerged or partially submerged orifices. So we have seen many things here. That is, first classification based on the size of the orifice and the head means height of liquid from the center of the orifice. So if the height of the liquid or head of the liquid is more than 5 times the depth of the orifice, it is called a small orifice. And if the height of the liquid is less than 5 times the depth of the orifice, it is known as large orifice. So here, head of liquid means height of the liquid surface. Again, depending on cross-sectional area, it can be circular, triangular or rectangular. Based on the upstream edge of the orifice, it can be sharp or bell-mouthed. Depending on the nature of discharge, it can be free discharging or drowned or submerged. Again, it can be fully submerged or partially submerged. To make the difference between small orifice and large orifice more clear, you can refer to the figure. So we have an orifice here on the side of a tank with fluid, and fluid is flowing through the orifice. So this is the head of the liquid H, which is the height of the liquid above the orifice. Okay, so above the center of the orifice. So if this H is more than 5 times the depth of the orifice, this is the depth of the orifice, that is the diameter. Okay, if it is 5 times the depth of the, more than 5 times the depth of the orifice is called a small orifice. And if H or head or height of the liquid surface from the center of the orifice is less than 5 times the depth of the orifice, then this is the depth of the orifice. It is known as large orifice. The depth of the orifice is given here. This is the depth of the orifice, D. So if H is greater than 5 times of D, it is called a small orifice, and if H is less than 5 times of D, the orifice is called a large orifice. Okay, now let's see the flow through an orifice. Consider a tank fitted with a circular orifice in one of its sides. Okay, so in the figure you have a tank with an orifice at the side. Okay, let H be the head of the liquid above the center of the orifice, that is indicated in the figure. This is the head of the liquid above the center of the orifice. You can see that it is measured, H is measured from the liquid surface to the center of the orifice. Okay, orifice is here. This hole is the orifice. Okay. The liquid flowing through the orifice forms a jet of liquid whose area of cross section is less than that of the orifice. That is, this is the jet of fluid, right? It is marked here, jet of fluid. So the diameter of the jet is less than the diameter of the orifice. Okay, so area of cross section of the jet is less than the orifice. Area of the jet of fluid goes on decreasing, and at a section CC, the area is the minimum. This section is approximately at a distance of half of diameter of the orifice. Okay, so the jet is the liquid flowing and its area of cross section is lesser, and at section CC is shown here. This is section CC. At section CC, the area is the least or the minimum, and this section is at a distance of half the diameter of the orifice. Okay, and in this section, the streamlines or the layers of the fluid are straight and parallel to each other and perpendicular to the plane of the orifice. This section is called the vena contracta. Beyond this section or after this section or after vena contracta, the jet diverges and is attracted downward by the gravity. You can see that in the figure. This is the orifice. This is the section of vena contracta. So when the flow reaches the vena contracta, all the streamlines will be parallel and perpendicular to the plane of the orifice or the hole, and also they will be straight. After this, they will be going downwards due to the gravitational attraction. And at the vena contracta, the area of cross section of the jet of fluid will be minimum. Okay, and also the vena contracta or section CC is located at a distance of half the diameter of the orifice. That is, this distance is half the diameter of the orifice. Okay. Now consider 2 points 1 and 2 in the figure. Point 1 is inside the tank and point 2 is at the vena contracta or at section CC. Okay. Let the flow be steady, that is dV by dt is equal to 0, and at a constant head h. The head of the tank is constant, that is h. Now applying Bernoulli's equation at points 1 and 2, we have P1 by rho g plus V1 square by 2g plus Z1, which is equal to P2 by rho g plus V2 square by 2g plus Z2. Now, Z1 is equal to Z2 because 1 and 2 are 2 points on the same horizontal plane. So there is no level difference or there is no vertical height difference between these 2 points. Hence the potential head or potential energy is equal. So Z1 is equal to Z2. So the Z term is removed from the equation, hence it becomes this much. So we know that P1 by rho g is the pressure energy that is equal to capital H, that is head of the liquid surface above the center of the orifice, that is indicated in the figure. P2 by rho g is equal to 0. See, at point 2 there is no liquid above the point 2. So it is atmospheric pressure. So P2 by rho g is equal to 0. V1 is very small in comparison to V2, as area of tank is very large as compared to the area of the jet of the liquid. This is derived from the continuity equation. In the continuity equation, we know that A1 V1 is equal to A2 V2, right? A1 V1 is equal to A2 V2, right? So 1 is inside the tank. So A1 is the area of the tank, which is very high. Area of the orifice is very small. So velocity at tank is very low, or velocity inside the tank is very low, and velocity outside the tank or velocity of the jet of fluid is very high. So V1 is very less in compared to V2. So we can take V1 as 0. So this equation we can write as P1 by rho g is substituted as H V1 square by 2g. V1 is very small, so we take it as 0. So the term becomes 0. Again, P2 by rho g is taken as 0 and V2 square by 2g is taken as such. So V2 is equal to square root of 2gh. This is the theoretical velocity. Actual velocity will be lesser than this value. Now let's see about the hydraulic coefficients. Coefficient of velocity CV, coefficient of contraction CC, and coefficient of discharge CD. Okay. The coefficient of velocity CV is defined as the ratio between actual velocity of a jet of liquid at vena contracta and the theoretical velocity of the jet. It is denoted by CV. So CV, coefficient of velocity, is equal to actual velocity at vena contracta divided by theoretical velocity. So V by square root of 2gh. So that is CV. The value of CV varies from 0.95 to 0.99 for different orifices, depending on the shape, size and head under which the flow takes place. Head is the height of liquid surface above the center of the orifice. Generally, the value of CV is 0.98, taken for sharp-edged orifices. Then you have the coefficient of contraction, which is CC, is the ratio of area of jet at vena contracta to the area of the orifice. So area of jet at vena contracta divided by area of orifice gives the coefficient of contraction. It varies from 0.61 to 0.69 depending on the shape and size of the orifice and height or head of liquid under which the flow takes place. General value of CC may be taken as 0.64. Next, we have the coefficient of discharge, which is CD. It is defined as the ratio of the actual discharge from an orifice to the theoretical discharge from the orifice. Okay, so actual discharge divided by theoretical discharge. It is denoted by CD. So actual discharge is Q and theoretical discharge is QTH. So CD is equal to Q by QTH. So discharge is area into velocity, right? We know that Q is equal to A into V. Q is equal to actual area into actual velocity divided by theoretical area into theoretical velocity. Okay. So this can be split up as actual velocity by theoretical velocity into actual area by theoretical area. Again, this is individually the coefficient of velocity and coefficient of contraction. So CD is equal to CV into CC. And the value of CD varies from 0.61 to 0.65. For general purpose, the value of CD is taken as 0.62. Now, let's see the experimental determination of hydraulic coefficients. Okay, first is the determination of coefficient of discharge, that is CD. How to experimentally determine or find out CD? The water is allowed to flow through an orifice fitted to a tank under a constant head H. So in the figure you can see that there is a constant head H. Okay, and on the side of the tank there is an orifice or a hole through which fluid is flowing outside. Our fluid in question is water. Water is collected in a measuring tank. This is the measuring tank. For a known time T. Okay, height of water in the tank is noted down. Okay, and actual discharge is obtained by multiplying area of the measuring tank into height of the water in the measuring tank divided by time T. Okay, and so actual discharge is obtained as such, and theoretical discharge is area of orifice into square root of 2GH. Okay. CD is equal to Q by A into square root of 2GH. That is actual discharge Q divided by theoretical discharge, which is equal to area of cross section into the theoretical velocity. Area of cross section of orifice is small a and theoretical velocity is square root of 2GH. Next, let's determine the coefficient of velocity CV. So, if you look at the figure, the vena contracta is at section CC, right? And a jet of water coming out from an orifice under constant head H is also shown. So, this is the jet. And it is coming from the tank where there is a constant head H. So you can see that there is a supply of water which ensures the head is maintained at level H. Okay. So consider a liquid particle. So you should consider one particle which is at vena contracta, that is here at section CC, at any time, and it takes position P along the jet in time T. That means a particle was at vena contracta when time T is equal to 0, and after time T it reached point P. P is here, this point is point P. So point P is at a distance of x from vena contracta, horizontal distance, and at a vertical distance y from vena contracta. So vena contracta is here, CC. Point P is here. The vertical distance between these 2 points is y and horizontal distance between these 2 points is x. Okay. So let's see. The horizontal distance traveled by the particle is x. So that is velocity of the particle or velocity of the jet, actual velocity into time t. So x is equal to v into t. So vertical distance y is given by half into g into t square. Okay, half into g, acceleration due to gravity, into t square. And from equation 1 we obtain t is equal to x by v from this equation. So substituting this value t is equal to x by v in equation 2, we get y is equal to half g into x square by v square. So finally we get v is equal to square root of gx square divided by 2 into y. Theoretical velocity is given as square root of 2gh. So CV is V by VTH, that is V is square root of gx square by 2y into 1 by square root of 2gh. So we get finally square root of x square by 4 into y into h, that is x by square root of 4 into y into h. So this is the expression for coefficient of velocity. Lastly, the coefficient of contraction Cc is given by Cd by Cv, because we know that Cd is equal to Cv into Cc. Then momentum correction factor is the ratio of momentum of the flow per second based on actual velocity to the momentum of the flow per second based on average velocity across a section, and is denoted by beta. So momentum per second based on actual velocity divided by based on average velocity. So that is momentum correction factor.